I've given quite a few of these summer school lectures in various places, and there is actually a book of Lazoo Notes, and probably the easiest way to find it is to go to my website on the University of Leeds. You can download it straight off for free, and it's all on there, so that's probably the best way in. So I'm going to talk today about planets primarily. And we're starting with the planetary science perspective. And the first thing to note is that we have a broad definition of planets, everything with a radius of about over 1,000 kilometers. The technical definition is that they've got to be still hot in the core, but not hot enough for nuclear reactions to be taking place. And that includes the larger moons as well as the conventional planets. So that's the list of objects that are of interest to planetary science. So these are the conventional terrestrial planets, and we include the 4 big satellites of Jupiter, and Titan, the biggest moon of Saturn, and Triton, the moon of Neptune. So those form a cluster, a group, and they're all usually discussed together when we're thinking of the internal properties of these objects, because they're all believed to have essentially the same structure, that is to say, an outer mantle surrounding an iron core. The gas giants are rather different. These are just Saturn and Jupiter, and many of the exoplanets that we have now discovered, mostly hydrogen and helium, probably with a small solid core. We don't actually know that for certain. Hopefully we will fairly soon when the Juno mission gets to Jupiter in 2016. But currently, it's generally believed there's a small solid core because it's very difficult to form the planets without them. And then the third category.
The gas, what is the density of the gas?
The average density of the gas giants is about 1. So Saturn would actually slightly less. Saturn would float in water in some sense, but Jupiter is just slightly higher. But the density, I will get onto that. I'll talk a bit more about that because that's quite an important aspect, is how the density varies throughout the object. And these ice giants are mostly water and ammonia, and we don't really know an awful lot about the internal structure of Uranus and Neptune, although we do know that they have magnetic fields. So I probably won't say very much about those objects. Well, let's just talk a little bit about how they actually form. The current view is that planets form from an accretion disk, and they're formed at the same time as the Sun, so they're basically the same age as the Sun. And star-planet formation, all part of the same process, so this is a very old idea. That rather nice picture there is showing you a star formation region there where new stars are being born in the Magellanic Cloud, which is a galaxy, a neighboring galaxy of our own galaxy. And as often with astronomy, the left-hand one is the picture of what you actually see. These are T Tauri stars. T Tauri disks are stars which actually are in the current process of forming, and probably planetary formation is taking place in these bodies. That's what they really look like. This is the artist's impression of it, and this sort of makes more sense. You can see the central condensing body there, which will turn into the Sun. You can see this accretion disk here, and the artist has sort of drawn some fanciful little lumps there, which are going to turn into planets eventually. The real thing has weird jets coming out here, and most of the object is obscured by dust, so it's quite difficult to see what's actually going on. So how do planetary systems actually form from protoplanetary nebulae? Well, that's a very active area of research, but it's still a very controversial one, and there are many unresolved problems. One idea is that the gas just accretes by gravitation. It's self-gravitating, and it just falls in on itself and builds up the planets. That may play a role, but another possibility is it forms small planetesimals initially, and those planetesimals, those small bodies, the sort of size of meteorites, collided together, stuck together, and formed larger objects. And certainly the diversity of planets suggests that collisions are very important. For example, Mercury has an exceptionally large iron core and a rather small mantle, so it may well have bumped into something and lost most of its mantle. The Moon, on the other hand, only has a very small iron core and probably got knocked off by a collision with the Earth when it was in the stages of formation. The discovery of exoplanets, of course, has made the whole problem even more complicated, because whereas we used to think that most planetary orbits were roughly circular, there are very many very eccentric orbits in exoplanets. So clearly, planetary formation can produce all sorts of things that happen outside our solar system, and our own planets are only a very specific sample of what we've got. So the low molecular temperature clouds contain dust and grains. The density goes up. The grains begin to collide and stick together to form larger objects. The process is not really well understood, but there's evidence, as I said, that it actually occurs. And then once you've got to that stage, you've got to these planetesimals of order 1 kilometer in size. These are now all in orbit around the star, the central sun. But many have got intersecting orbits, so they tend to collide, leading to impacts, which, because they're all in the same orbit, typically, they don't have very different velocities, so they're fairly low velocity impacts, which result in bigger objects. And this can be modeled, and indeed is modeled, by using n-body integrations of numerical integrations of planetary orbits, showing how quickly this process actually takes place. And after that, there are sort of late-stage collisions. So over the last sort of 10 million years or so, you get large-scale impacts, and these are the things which you can see evidence of. Of course, you can, if you look at the Moon, it's still absolutely full of craters that have been there since its formation. And then there are many observations which suggest that a lot of collisions actually took place at that stage. There's also evidence that planetary migration happens. That is to say, it's not clear that the planets are actually where they were formed. Certainly, some of the hot Jupiters that are seen in exoplanets, it's almost impossible to explain how they could have formed actually where they are. So what we believe is that they were formed out in the outer regions, like our Jupiter, and that they then migrated inwards because there's still quite a bit of gas lying around there, and the interaction of the gas and the planet can make the planet actually spiral in. But it's, as I said, it's still a lot of stuff up for grabs there. Okay, so once we've got to this stage, the next thing that's important that happens for terrestrial planets is this process that's known as the...
Can I ask one stupid question?
Yeah.
So when the planets are forming,
yeah.
They remain disk for a while, or they become spherical very quickly?
They tend to become spherical quite quickly, actually. We believe that these things sort of form these objects about 1 kilometer apart, so those will be just sort of things like meteorites and asteroids are now, sort of irregularly shaped, but as they collide together, they tend to, the gravity becomes very important very quickly, so they become quite spherical quite quickly. The whole process of these collisions happens really remarkably quickly, actually, compared with the whole age of the planetary system, which is 4.5 billion years. But of course, as a result of all these collisions, everything gets extremely hot. So we start off from having a large amount of energy, gm squared over r, present at the formation. And if you work out what that is, and then you think about how much heat is actually coming out, for example, of the Earth at the present, we know there's about 45 terawatts coming out, and you ask yourself, how long would it take to get rid of this amount of energy if it's coming out at 45 terawatts? And the answer is a lot longer than the age of the solar system. So that's why these things are still hot. They're cooling down, but they're cooling down at a fairly slow rate compared with the enormous amount of heat which was generated right at the beginning. So the heaviest element present in large quantities is iron, and that seems to have made its way to the center of the planet. Again, that happens at a fairly early stage, releasing yet more gravitational energy, and producing the basic structure of the terrestrial planets which we have at the moment. And this heat of formation is actually the most likely energy source for planetary dynamos. So if you want to know what is maintaining that magnetic field against ohmic dissipation, the answer ultimately is it's the heat of formation which is still there. The convection is carrying that heat flux outward, but there was so much that they haven't yet cooled down. Now, one complication about this whole story is that radioactive elements are known to be present in the mantle and contribute a considerable part of the heat coming out of the Earth's surface. I've got 44 terawatts. I think that's slightly out of date. I think it's 46 at the latest value. Did the differentiating ion take any radioactive materials with it down into the core? Now, that is entirely possible. There are things like uranium and radioactive potassium, which is certainly not present in the mantle. But there are two possibilities, of course. It might, at the formation state, have just evaporated into space, or it might have got taken down with the ion and be still there in the core. And this actually makes quite a difference to your thermal history model, because if there is radioactivity, then, of course, the core is cooling down considerably more slowly, because there's quite a lot of heat still possibly coming out of the radioactivity, although that will gradually decay away over time. So that's one of the unknowns in all this subject, and of course it may be that in different planets there are different concentrations of radioactivity. It may be that in fact there's very little radioactivity in the core. We really just don't know at the moment. They do have implications for how the solid inner core of the Earth is formed and grown, and they also have implications about the amount of energy available to drive a dynamo. So possibly the best way of finding out the answer to those questions is to deepen our understanding of the way in which the magnetic field is actually generated. So here's what we've got after all this process. So this brown region here is the liquid iron core of the Earth. This grey region there is the solid inner core of the Earth. I'll explain in a minute why the hottest part of the Earth is actually solid, which is slightly surprising at first, because usually when you heat things up they melt, but that's the way it is. This is a model of the interior structure of Ganymede, which is sort of slightly different because it's got a sort of ice layer outside and a mantle layer and a core inside there. So basically the reason for the solid inner core is because the pressure raises the melting point. So what do we think the energy sources for the dynamo are? Well, the most popular solutions are what are known as thermal convection and compositional convection. I'll say a bit more about compositional convection in a second. But these are two sort of tidal interactions and precession of what you might call outliers, but they're nevertheless very interesting ideas, and it may be that they do play a part in at least driving the dynamos of certain planets. So let me just explain briefly what these are. Well, thermal convection, of course, is simple in the sense that there's lots of heat to get out. It gets out by mass motion, and that's just thermal convection, and that thermal convection can stir the core. When you've got a solid inner core, then all the time as the planet cools down, the solid inner core is growing because the whole planet is cooling, and therefore the core would get bigger and bigger. The core is comparatively pure iron, and the inner core is comparatively pure iron, so that in the solidification process, light materials are released at the core mantle, at the inner core boundary. And those light materials could be buoyant, and they could stir up the core as well. And the most popular view is that it's a mixture of thermal convection and compositional convection. Compositional convection is probably dominating right now. So what about precession and tidal interactions? Well, perhaps the most popular is the precession idea. It's well known, of course, that the torques, because the Earth is non-spherical, the torques produced by the Sun make the axis of the Earth rotate around once every 26,000 years. So it spins around in addition to its daily rotational motion. And of course, the liquid outer core has got to somehow keep pace with this precessional 26,000-year motion. And that, of course, is going to, in order to do that, there's got to be coupling between the core and the mantle, and that will stir, a coupling process will certainly stir the interior of the liquid iron core, and that stirring process could generate motion, which could generate magnetic fields. Tidal interactions are sort of basically the same kind of mechanism, except we're just looking here at the very short period tidal interaction between the moon, which of course the solid Earth is continually changing its shape as it rotates around under the moon's and sun's combined gravitational potential. It's a small amount, but the outer core must be doing the same thing, and so again that could give rise to an energy source. And it turns out that there's a lot of energy in this rotational motion, so there is actually enough energy there to drive the dynamo. But whether that energy that motion can be converted into useful motion for dynamo driving is still not entirely clear. But there are people working on that, and indeed there's a big precession experiment being built right at the moment in the Dresden group there with Frank Stefani, and that's going to be a great big precessing sphere, well, precessing cylinder, isn't it? And it's going to move around, and it'll certainly stir up the fluid, and it's got liquid sodium in the middle of it. It will have liquid sodium in the middle of it, so who knows, that might actually turn into a dynamo and a magnetic field. So let's talk a little bit about this convection. The core, I've already mentioned what compositional convection is, so I don't need to go through that again. I just mentioned that the light material that's released in compositional convection, so as the sulfur and oxygen are released, almost pure iron solidifies onto the inner core. And this stuff, this light material, it may just mix into the outer core and just gradually lower the outer core density, or it might actually make its way right through the outer core, like a sort of smoke in a smoke-filled room rises to the top, and it might have collected below the core mantle boundary. It's sometimes called a stably stratified inverted ocean, because it would be a light layer of material up against the core mantle boundary. And so Braginski calls it rather imaginatively an inverted ocean. Or, as I said, it may just mix. But there's a lot of interest in these possible stably stratified layers, because stably stratified layers can alter the dynamics in interesting ways. They change the wave properties. So that's quite a hot topic too right at the moment, examining the different dynamics of inverted layers. Okay. If there's probably small radioactivity or no radioactivity, you can work out what the rate of cooling is, and you can also work out then when the inner core is likely to have first formed. And it turns out that it's only a billion years ago, and the whole thing is 4.5 billion years ago. And the oldest rocks that are magnetized are 3.5 billion years old. So the inner core is actually younger than the oldest magnetized rocks. So clearly the dynamo was working before the inner core formed. So if you've got a dynamo theory which relies entirely on the inner core, you're in a bit of trouble there, explaining exactly how it came to work before the inner core was actually formed. So again, the formation of the inner core and the growth of the inner core is a sort of interesting whole part of the thermal history of the Earth, and it's sort of all relevant to dynamo theory. Well, I need to say a little bit about mantle convection. I mean, one could give 3 hours of talking entirely about mantle convection with no trouble at all. But the large density jump at this core mantle boundary and is because it's below it's iron, which is quite a high density, and then there's a very sharp transition which you can pick up by looking at the seismic waves which pass through the center of the Earth. The Earth appears to be the only planet that currently has plate tectonics. That's mantle convection. So although it's solid on short time scales, of course, it can flow on extremely long time scales, and this shifts the plates around on this kind of time scale. And this transports the heat in the interior to the surface. Now, of course, some of that heat flux will be going through the core mantle boundary from the outer core. We don't really know how much, to be honest. That 10 terawatts is a guess. Numbers as low as 3 terawatts have appeared in the literature, and numbers as big as 15 terawatts have appeared in the literature. The current philosophy is that it's quite high, so the 10 to 15 guys are in good shape at the moment, but who knows what's going to happen next. So that's the heat flux at the CMB, and that's of course important because that gives you an idea of how much convective flux is being carried out. Not all of it will be convective, as I'll show you in a minute, but it gives you an idea of the convective heat flux carried out, and that's of course very important for the dynamics of convection and hence for the dynamo. So some of these plumes are coming out of the core mantle boundary because there are sort of hot spots where the flux is coming through, and some of these plumes may rise right through the mantle, and some people believe that they're actually emerging in sort of hot spots like Hawaii, going right through. That's sort of a picture of whole mantle convection. But most of these things, as I said, are quite controversial still.
How is something solid on some time scale and fluid liquid on some other time scale?
Other time scale, well, it's sometimes called solid state creep, I guess. I mean, I believe it's true that even a material like glass, if you leave it for long enough, it actually flows. So things do flow on a very, very long time scale if there's a continual source of heat. Yeah. So, yeah, okay, but it's extreme. What is very difficult is to get a relationship between the elastic strength, the viscosity, and the forces involved, so that the constituency relations are very difficult to actually formulate, and that's why mantle convection is such a difficult subject. Actually, it would be nice.
Materials you can make a cornstarch solution.
Yes.
So the cornstarch is, if you hit it with a hammer, it's rubber.
Mm.
Otherwise
Yeah, it will flow. Yeah, it's the same. Yeah, so these are all materials which are non-Newtonian materials, basically. That's the crucial thing. Okay, right. So, yeah. So when does thermal convection occur? Now, this is important to understand this. It only occurs if the heat flux produced is greater than the amount that can be carried by conduction. The way you test whether convection is actually going to occur or not is you work out what the adiabatic temperature gradient is. That is the temperature gradient that you get if you're exactly in adiabatic equilibrium. That is to say that there's no net buoyancy force if you move particles of fluid up and down. And that is given by this formula here, where alpha is the coefficient of expansion and Cp is the specific heat. So that defines the adiabatic temperature gradient. And in the outer core, that's about, what is it? It's about 1,000 degrees jump over about 2,000 kilometers. So that gives you what the adiabatic gradient is roughly. So if the heat flux carried down by this gradient by conduction is then that, yeah, where kappa there is the thermal diffusivity. So that's the one that's got the units L squared T to the minus 1. So then from that formula, you can work out how much heat flux is actually carried by conduction, combining that and that. So then that gives you a fairly simple formula for the amount that can actually be carried by conduction, and you'll only get convection if the actual heat flux is greater than the amount that can be carried down by conduction. And this, straight away, is the simplest explanation of why some planets have magnetic fields and other planets don't have magnetic fields. So the simplest answer to that question is your core convecting? The answer is yes, if F is greater than F add. If your core is not convecting, possibly like in Venus, for example, which doesn't have a magnetic field, then the simplest explanation is that all the heat flux coming out of Venus's core is actually carried down by this conduction process, and convection is never occurring. So the core is never being stirred, so there's no energy source for the magnetic field, so there's no magnetic field. So looking at that formula there, you can see that it's entirely reasonable that two planets which look quite similar, Earth and Venus, actually have different heat transport processes in the core, and hence one will have an energy source and the other does not have an energy source. And of course, in the case of Venus, what is happening is that there's no mantle convection, there's no plate tectonics going on in Venus, so the amount of heat coming out of the core is probably less than it is on Earth. So that in a sense, it's the mantle convection which is essential to drive the dynamo, because if it wasn't for the fact that this heat flux is being taken out quite efficiently through the mantle, then the amount of heat flux coming through the core would be less than the adiabatic value. There would be no convection in the core, and probably nothing would be happening there. So,
repeat the argument. How is Mantle helping strong convection?
Because it's all a question of getting the heat flux out. If you didn't have any mantle convection, then all that happens is that everything gets essentially isothermal in the core. I mean, it just if there's no heat flux coming out at all, then the conduction will just lead you to a state where there's essentially no convection is taking place. So it's that criterion which tells you straight away that some planets are likely to be convecting and have magnetic fields and others are not. So this is a picture of the geothermal. I don't totally like this because I don't think the numbers are quite right, but it's qualitatively right. Here is the temperature gradient, as this is depth as you go down from the surface here to the center of the Earth here. This region here is the inner core. This region here is the fluid outer core. This is the mantle here. Now you can see that this is the melting curve for iron. So iron is liquid on this side and solid on this side. And you can see that the actual temperature gradient, which is very close to the adiabatic temperature gradient, cuts this curve here. And on this side we have solid, and on this side we'd have liquid. So that's why there's liquid here, and that's why there's solid there. And that's why the inner core is solid, even though it's in the hottest part of the Earth. And then here there's this boundary layer just above the outer core, which is sometimes called the D double prime layer. This is basically where the mantle convection is starting. So that's the bottom boundary layer for the mantle convection. And the melting curve for the mantle. So we're all on the right side of this one, so we have a solid mantle rather than a completely liquid mantle, which if you turn those things around, you would get.
Sorry, for lower temperature, you should have solid, right?
Yeah, lower temperatures, you have solid, that's right. So this is where we are in reality. That one there is the critical point for melting. So we're currently solid. If you go back in the...
Iron is the other way around. So why is it not melting?
Sorry, this one lies on this side. So this is the actual Earth is here. Yeah. So this is anything to the left of this one is solid. Anything to the right of that one is liquid. Yeah.
Right,
Yeah.
but for melting curve for iron,
For the melting curve for iron, yes. And if everything to the right is liquid, yes. So that's the liquid outer core. Everything to the left is solid. So that's the solid inner core. Yeah. That all makes sense.
right.
Yeah.
In the mantle,
In the mantle.
itself,
Oh, we don't have any iron in the mantle, so that's the reason we don't want to worry about that. That's just the theoretical line. Yeah, perhaps we should have deleted that bit. Okay, if you go back in the past, of course, everything was much hotter, and it's entirely possible that the actual thing could have been on that side of that curve. So that's sometimes called the magma ocean theory, where the idea is that part of the mantle might, in the early stages, have actually been liquid. And that's a recent idea that's going around. Okay. Now, there's something called the Wiedemann-Franz law, which is important. This is a physics thing and tells you basically that there's a relationship between the thermal diffusivity and the magnetic diffusivity, eta here, and they're related by this formula here, which basically comes around because the same electrons that give rise to thermal conduction also give rise to electrical conductivity, and that's basically why these things are related. But from our point of view, there's an interesting thing here, because you might imagine that to get a dynamo going, the best thing possible would be to have eta as small as possible, so you have a little magnetic diffusion, a high magnetic Reynolds number, and that would be extremely good for dynamo action. But you've got to be a little bit careful, as Stevenson pointed out, because if you make eta very, very small, that makes kappa very, very large. And if kappa is very, very large, if we just flip back to here, you'll see that the amount of heat that can be carried by conduction gets very, very large. And it then becomes very unlikely there'll be any convection, because all the heat's being carried out by all this high-powered conduction, and so there's nothing left to actually drive the dynamo. So you've got to be very careful in planetary dynamos, or certainly for terrestrial planets, to have a value of eta which is not too small. I mean, you want it to be small because otherwise you've got too much ohmic dissipation. So you don't want to be too small, but on the other hand, you don't want to be too large, because, of course, if it's too large, the magnetic Reynolds number's too low and you'll never get a dynamo. So you've got to get eta the right sort of value so that it's still conducting, but it still manages to make a dynamo. And the Earth certainly seems to sit in the right ballpark for eta, and that's just very fortunate for us dynamo theorists. So that's sometimes called Stephenson's paradox, because a high electrical conductivity you'd think would be good for dynamos, but too much electrical conductivity is actually bad for planetary dynamos. And I mentioned about Venus. Venus's surface looks, well, recent, I say about 500 million years, because it's got a lack of cratering compared to the moon, but there's still a lot of cratering there, so we still know that it's very old. Possibly Venus undergoes periodic resurfacing, so the models generally suggest that the heat from radioactivity and cooling builds up in the interior, and then eventually the whole thing sort of turns right over and goes liquid. And at that point, there'll be lots of heat coming out of the core, and so at that point, it may even be that Venus has a dynamo, but then it all shuts down again when it all solidifies, and the mantle convection goes down, and so then all the heat can be carried by conduction throughout.
What is the heat source for the Earth?
Well, the main heat source is the initial. It's right at the initial bombardment. There was gm squared over r, and if you work out what gm squared over r is, it's very big. Although there's a lot of heat flux coming out, it hasn't had anything like enough time to get rid of all that gm squared over r. So that's basically where the source of the energy is. Well, what about Mars? Mars has got two very different hemispheres. So there's a southern hemisphere and a northern hemisphere, where the topography of the thing looks really rather different. So this is the northern hemisphere, and this is the southern hemisphere. Interestingly enough, when the probe went round Mars, it had a magnetometer on board, and it measured the magnetic field of Mars. And since Mars doesn't really have an internal dynamo at present, it was expected that there wouldn't be any magnetization, but they went looking for it nevertheless. And it actually turned out there's quite a considerable amount of crustal magnetization in Mars. So it almost certainly did have a dynamo at one stage, because it's very hard to explain how you could get that magnetized surface if there wasn't a dynamo in the past. And here is this one here. This diagram is rather unfortunate, because this longitude here is slightly different scale from this longitude here. But I'll show you how these pictures correlate in a second. But this is the magnetic picture, so there's quite a lot of action in the southern hemisphere. not so much in the northern hemisphere. And something funny has happened in Mars. Some kind of global convection has presumably happened. Some kind of L=1 global convection has happened in Mars to produce these two very different hemispheres. And the magnetic field can be dated because this object here, that was formed when something big crashed into Mars, and it's that which is a magnetic hole, so it demagnetized that part of the crust where it actually landed. So when it remagnetized, it was presumably not, the dynamo had died by then because it remagnetized without any magnetic field in it. So from those kind of arguments, we can roughly date the time at which the Martian dynamo switched off, and it's usually thought to be about 350 million years after formation. So the first 350 million years of its life, Mars had a dynamo like the Earth, and presumably an external magnetic field like the Earth, but then it petered out. And we can ask, why did it peter out? And the most likely explanation is because the heat flux went down below that critical value. So if the heat flux goes down below that critical value, which all the heat can be taken out by conduction, then no more convection, no more dynamo, and that's it for the magnetic field. The strength of this, I can't remember exactly. All I remember is it's actually larger, I think, than the crustal magnetism of the Earth, which is sort of, it's really a lot stronger magnetization. It's a bit of a mystery, actually, I think, why it's quite so strong as it is. And it's certainly completely unexpected, but there you go. So that's what happened in Mars. I don't think I need to go through that again. So let's talk about the structure of the giant planets. So these here, this is a speculative rock and ice core here in these planets in order to get them to accumulate and form. Then there are two regions here. It's all hydrogen and helium, but there's a very important layer here, distinction here, because down here the pressure is so high that the gas becomes something called metallic hydrogen. Because particles are being squashed so close together, they start to move faster because you can't get more than 2 fermions into h cubed of phase space. So if you try to squeeze them physically together, then they start moving up in velocity. If they start moving up in velocity, they start colliding and they start knocking electrons off, so they become ionized. So because of this metallic hydrogen property, these things here are electrically conducting, even though it's a gas. Now, you wouldn't expect hydrogen or helium to conduct electricity, but it does if you compress it to such an extent that it goes into this metallic state. So out here we have the ordinary molecular hydrogen helium, which is almost non-conducting by comparison, and then this thing here, we have a sharp transition from where we go. So it goes, I shouldn't say exactly sharp transition, it is continuous, but it suddenly starts to rise, the conductivity suddenly starts to rise very, very rapidly and saturates in its interior value. And the same thing happens in Saturn. The only difference between Saturn and Jupiter is we think there's a mixed layer here, which is stably stratified, and that's to do with the properties of hydrogen and helium at very high pressures, and I'll say a little bit about that later. This is all speculation, but since Uranus and Neptune have magnetic fields, they've pretty well got to have something that's conducting. So the usual view is that this is some kind of an ionic ocean, again caused by the high pressure, and it's believed that water and ammonia mixes can start conducting electricity at these sort of pressures. And there's some evidence of this from high pressure physics. So that's the basic structure of those, and that's about metallic hydrogen. I've put a few references there. There's the famous stellar structure book of Kippenhahn, Weigert, and Weiss, 2012. That explains all about the increase in the particle velocity, because the same thing happens in white dwarfs. So that was where it was discovered first. So You can get a description of all this. And high pressure physicists have now developed very sophisticated equations of state so that they're actually solving by quantum mechanical methods for what the pressure and the density and the temperature are, and the electrical and thermal conductivities are now coming out of these calculations. Quite recently, it has to be said. So we now have actually specific calculations based on quantum mechanics of what the electrical and thermal conductivities in the ice giant, in the gas giants are. So what sort of models do we use for looking at planetary gas giant models? So these are polytropic models. If you don't know what a polytropic model is, you probably want to look it up. Again, in stellar structure books are probably the best place to do this. So I'm not going to go through this in any detail. I'm merely going to point out that polytropic indices in planets tend to be quite small. So n equals 1 or n equals 2 is the sort of value we're usually thinking of. But they do span a vast range of density difference. So the density near the outer layers is very, very much lower than the density in the inside. So if you want to get a dynamo model of the whole convective region, you really have to take into account the varying density, which Boussinesq models don't. So that's why we've moved to doing anelastic models, and I'll talk about those two a bit later on. But the reason why you need anelastic models is this huge density variation as you go through the planet. Oh, and there's a little plot of log rho there against the radius, and that's the sort of typical of that thing you get from a polytrope. So again, it's going down. The actual real one, calculated from these equations of state, it drops off even faster, actually, than the polytrope ones down near the surface. But all these things, you can see that since this is a logarithmic scale, the density down here is hugely less than the density up there, whichever model you actually have. Okay. And the temperature structure there, well, a polytrope isn't a terribly good model, actually, for the temperature structure. And that, well, a perfect gas polytrope isn't at all a good model because this degeneracy pressure that comes from the quantum effects actually takes over up here. So the temperature isn't anything like as high as you might think if you actually did a polytropic model. So, yeah. This left figure, this is coming out of these quantum mechanical calculations. So basically, we've got an equation of state, which gives you the pressure in terms of the density and the temperature, yeah, coming out of these quantum mechanical calculations. And all the sort of relevant thermodynamic coefficients, all the differentials are also given by this model too.
You don't assume that the fluid is moving.
No. This is all in the equilibrium. So this is all these calculations are done assuming you're in hydrostatic equilibrium and that you're actually adiabatic too. That's again part of the. The previous one, yeah. The definition, yes. That is this polytrope. Yeah, there's a slight subtlety here. There are two kinds of polytropic models used in stellar structure. One is the Lane-Emden equation, which this is not, and the other is the model where you're centrally condensed. So you assume that the gravity field is gm over r squared, and that is the formula. That very simple formula is what you get if you use that assumption. So the distributions are two distributions are slightly different. Gm over r squared. Well, it's sort of convenient because then you get these very simple formulae, basically. So everything is then analytic and definite. So that was what we used for the benchmark because we didn't want everybody sort of messing around with different equilibrium models. So it's simplest to take an absolutely definitive model, which everything is explicitly given by. So that's the reason for that. Not particularly realistic. I mean, you could see. I mean, it's the difference between that. I mean, and you can see this one is sort of fairly concave, and that one's sort of fairly convex that way. So there are differences. It doesn't turn out to make an awful lot of difference, actually. People have tried with both of these profiles. The crucial thing is to have the big range of density. Yeah?
Is the rate of change of going down important? Like, is it exponential downfall, or like maybe 1 over x to the power of
It's 1 over x to the power, yeah. So it's not an exponential drop-off. Well, it is very near the surface. Very near the surface is an exponential drop-off. But in the interior, it's more like a power law.
How can we integrate that? How are these two things different? Like exponential downfall and 1 over x to the power?
Oh, well, it all depends on the... it comes from the equation of state, doesn't it? And I mean, you're in the interior, you're assuming it's following the adiabat, yeah? And then when you get close to the surface, you switch off that adiabat onto essentially onto a near isothermal atmosphere, and that's really what is the difference between an adiabat and an isothermal atmosphere that produces that difference. And this is what I said about the electrical conductivity. So this is the diffusivity. You see the diffusivity is quite low in the metallic hydrogen region, and then it zooms right up. This is a logarithmic scale here. It zooms right up. And when you get into the molecular region, it's essentially not conducting at all. So that's the sort of model we're actually using in our dynamo models. Right. Stably stratified layers, well, that may be important because, of course, that will change the heat flux. If there are stably stratified layers inside the giant planets, then things are likely to be different. And it's believed that Saturn has a stably stratified layer in its interior and that Jupiter doesn't, and that this is why the magnetic fields are rather different. So I don't want to go too much into detail about that. I'll just mention the gravity field. Andy Jackson mentioned how you expand the magnetic field yesterday. The gravity field is also expanded in spherical harmonics. And the reason this is significant is that Juno is going to measure the gravity field very accurately when it arrives just over a year from now, assuming it works, of course, because the rotational force, the centrifugal force, affects the magnetic mass distribution. We may be able to find out what the internal rotation rate is by actually calculating what the gravitational field is, because these two are actually connected. So the hope is that by measuring the gravitational field extremely accurately, we'll then get a better idea of what the rotation rate inside these planets actually is. And that's actually quite a controversial thing, which I'll just talk about briefly now. So Jupiter and Saturn have belts and zones which are associated with east-west zonal flows. These east-west flows, they're independent of longitude. It also has long-lived storms, such as the Great Red Spot on Jupiter. And the issue here is what is driving these winds and why are they so different from the winds on Earth? And the crunch question is, are the winds just on the surface, or do they reach deep into the planet? And this has been an extraordinarily controversial issue for 30 years, I guess. And that's one of the reasons why they're sending Juno off there, is to measure this gravity field, which will hopefully put an end to all these people arguing about whether the zonal flows are shallow or deep. So that's what Jupiter looks like. So it's got the belts, but the belts are also associated with the zonal flows, and the zonal flows are going it's going this way in the equatorial, and then there's a belt going that way there, and then in here it's going that way, and then it goes that way. So we can actually sort of see that described out here. So that's the latitude here, yeah, and that's the wind speed, and you can see it's prograde, that's with the rotation in the equator, and then there are these retrograde jets here, and then out here there's lower amplitude stuff, but an oscillation of prograde and retrograde. And Saturn over here is sort of similar. There's some variability in Saturn, there's very little variability in Jupiter, but this also seems to have evidence that there are bands as well as in Jupiter. So those are the zonal flows. The Galileo probe was the first thing that tried to work out this controversy about whether the flows go deep into the interior or not. and it gave a positive result. It entered at 7 degrees north into the eastward equatorial jet, and you can see the wind speed actually increased as he went down. So that supported the deep people, because as he went down deeper and deeper, it went faster and faster. But of course, the shallow people immediately responded by saying, well, this thing's only got to 20 bars. The interior of Jupiter is megabars, yeah. So if you went down here, you'd see it all shallowing off and going back down there. Well, that may be true, of course, but we just don't know. So there's arguing between that. Interestingly, the ice giants go the other way. So at the equator, they go westward, whereas in Jupiter and Saturn, at the equator, they go eastward. Another of the great mysteries of the solar system, which we haven't really resolved yet. So that's one for us. That's a model there. It has to be said that, okay, it's a model, but it doesn't actually agree with the basic physics of even what we know of the ice giant planets. So I'm not really totally convinced by that model. It's a pretty complicated question, is that. So with Jupiter, with a large radius ratio, that's the metallic region there coming in there. So there's a comparatively narrow band there, and the suggestion has been, which I believe actually, that height there is associated with these much stronger zonal flows there, and these much weaker zonal flows up there are associated with the behavior up there. And then that sort of fits with Saturn because that's got a much broader equatorial band, and it's got a much deeper metallic region. So the metallic, because the pressure in Saturn is less, you only get to metallicity about here, whereas at about 0.6, whereas in Jupiter it's about 0.9. So what does Jupiter's magnetic field actually look like? Well, that's a plot of the radial field at the surface of the planet. Now, that's not at the core mantle. The core mantle boundary would really be down where the metallic hydrogen region starts. But of course, in Jupiter, that's not all that much below the surface because it's only about 0.9 of the radius is the metallic electrically conducting region. So it's probably not all that different from that actually down at what you might call the core mantle boundary too. So it's a strong field. It's basically a dipolar field, plus and minus. There's quite clearly a fairly strong m=1 component to the field, which there isn't to the Earth's. If you remember, the Earth's field had those strong patches that Andy Jackson showed you. So it's more like m=2. And the dipole is tilted at about 10 degrees, which is broadly similar to the geomagnetic field. Big surprise is that Saturn's magnetic field is completely axisymmetric. As you can see from that picture there. Why is Jupiter's field and Saturn's field so totally different when we all believe that Saturn was just a sort of slightly small, younger brother of Jupiter? Well, it's probably because of the stable layers inside, because the stable... this is axisymmetric. Jupiter is quite non-axisymmetric. But Saturn, it's so axisymmetric, in fact, that you can't actually tell, you can't actually see any non-axisymmetric components. You can't see any cos m phi's or cos m or sin m phi's other than m=0. And this is a bit of a disappointment, really, because you can work out something about the internal rotation rate of Jupiter, because as the planet goes round and round, it carries this non-axisymmetric field with it. So the magnetic pole sort of sweeps round and round as the planet rotates, and you can see that. So by seeing the frequency with which that sweeps round, you get an idea of what the actual internal rotation rate is deep inside the magnetic core. And that's pretty constant, and that probably suggests that the zonal flows don't actually go down right into the magnetic region. They may go deep down into the molecular region, but probably not into the magnetic region because of that observation. They were hoping that they'd do the same thing with Saturn, and that's one of the Cassini mission objectives was that. Unfortunately, it failed because the wretched field is completely axisymmetric, so you can't tell. It doesn't sweep. the magnetic axis doesn't sweep around. It just stays there and just rotates around, and that just doesn't produce any signal. So we still really don't know what the internal rotation rate of Saturn is. Although there are lots of papers speculating on what it might be, of course, as you can imagine. So why should it be like that? Well, we believe that there's a stably stratified layer in the conducting region, and that's got a zonal flow which is somehow wiping out all the non-axisymmetric components. Because, as I'll show briefly, it is actually impossible to generate an exactly axisymmetric magnetic field by dynamo action. So that's known as Cowling's theorem, and is a very important piece of dynamo theory. So Saturn cannot have an axisymmetric field everywhere. If it did, it couldn't be a dynamo. So what we think is actually happening is that it is non-axisymmetric in the interior, but because of these stably stratified layers, the non-axisymmetric components are wiped out, and so they're not on view for us looking from the outside. If we went into the middle of the planet, we'd see the non-axisymmetric components, which must be there because of the need for them in order to generate the magnetic field by dynamo action. And the ice giant fields, well, it wasn't expected that they'd have magnetic fields at all, and the magnetic fields they have are quite strong and very bizarre. They're not at all dipolar, they're not quadrupolar, they're just a mixture of dipoles and quadrupoles. So these have got all the spherical harmonics in a sort of fairly random sort of way. Again, a very unexpected result, but a very interesting one as well, and tells us that whatever is going on in the interior of the ice giants is quite different from what's going on in the gas giants. This is a very recent one. I'm sorry it's a bit rather rubbish quality. I don't know quite why that happened. But that's Mercury's magnetic field as the messenger has just been in orbit round, I think it still is in orbit around Mercury, and is sending back stuff about the magnetic field. And that, again, was a bit of a surprise. These things nearly always do turn out to be a bit of a surprise. It was known that Mercury had a magnetic field, but it was thought it was basically dipolar. But actually, it's very asymmetric between the two hemispheres. So it's actually a sum of dipole plus quadrupole in such a way that they add together, the quadrupole adds together up there, and the quadrupole and the dipole subtract off there, giving a much weaker field in the southern hemisphere than in the northern hemisphere. And that's sometimes called a hemispherical dynamo, because it's basically all the dynamo action. The magnetic field is being generated primarily in one hemisphere. And as we see, that is something that can happen in dynamo models. I should imagine it's microtesla, I would think. It's oh, millitesla. Oh, it's not as much. There's not as much as that. It's not as much as that. It's not as much as millitesla, no. If it says that, it shouldn't. It's a lot weaker than I can't remember offhand, but it's certainly a lot weaker than the Earth's magnetic field and much weaker than Jupiter's magnetic field. It's probably microtesla, I should think. Okay, so let's see some questions about major problems in planetary dynamo theory. Why is Mercury's field off-center and so weak? Well, that's an interesting one. Why does Venus not have a magnetic field? Well, I gave an answer to that. I mean, that's probably the right answer, but of course the other possibilities as well. Why are most planets dipole dominated, and well, why do geomagnetic reversals occur? That's another interesting question. What powered the Dynamo 4 in a core formation? Well, possibly it was just the heat coming out, so it possibly all thermal convection at that stage rather than compositional convection. But certainly some of the models, there's some difficulty getting enough energy from the heat alone without the effect of the composition. So Mars evidently had a dynamo at stage. What killed it off? Well, I think we probably know the answer to that. It probably stopped convecting. Ganymede has a dynamo. It's got a magnetic field. It's the only moon of Jupiter to have a magnetic field. The other three, well, Io has a magnetic field, but it's so close to Jupiter's very strong magnetic field that it's very difficult to tell whether it's got its own magnetic field. It's thought probably doesn't. But because it's swamped in Jupiter's magnetic field, it makes it a bit tricky. Ganymede definitely does have its own dynamo. It has its own magnetic field. But nevertheless, that's quite a surprise because its core is quite small, and so you might imagine that its magnetic Reynolds number will be rather small. But it nevertheless is clearly big enough in order to get a magnetic field. Why is Saturn's field so axisymmetric, and what on earth is going on in Uranus and Neptune? So a whole slew of questions there, all waiting for people to have a go at. I'm not really going to talk about the solar dynamo.
So in
Yeah.
the metallic, this Jupiter, is there flow of metal inside when the
Oh yes, it's all convecting inside Jupiter, yes. So it's undergoing convection. And we think we know that the speed of the convection is a little faster than the convection on Earth. You can kind of get an idea of what the convective speeds must be because they've got to get the heat flux out, and we know what the heat flux coming out of the planet actually is. So you can get an estimate of what the velocity actually is from the amount of heat that's actually being carried out. Although I should say there's a caveat there. In order to do that, you do have to have a theory of convection. That is to say, you have to know, you have to have something like mixing length theory, Prandtl's mixing length theory, or if the thing is rapidly rotating, then you have to have an equivalent to Prandtl's mixing length theory, which is valid in a rapidly rotating planet. So there is, I mean, when I say we can get an estimate of the velocity, there's still a band of uncertainty there because of our ignorance about rapidly rotating convection and the heat transport in rapidly rotating convection. But we'll come back to that in next. Oh yes, yeah, I'll come on to that. That's my next topic after this. This is starting off by giving you a sort of overview of what the observations are and what we see, and then I'll go on to on why it's like it is and what we know about the theory. So I'll just say a very little bit about the solar dynamo. So there's a radiative zone, so there's convection going on out here in the outer 200,000 kilometers of the sun, and that is stirring the gas up so that there's lots of motion there. It's highly ionized in the interior and fairly ionized at the outside, so there's lots of electrons floating around to give you lots of electrical conductivity. So the magnetic Reynolds number for the sun is enormous, and the velocities vary from a few meters a second down to several kilometers near the surface. So there's loads of motion going on, stirring it all up to give you a dynamo. We have the famous observation of the 22-year butterfly diagram. The magnetic field emerges at sort of latitude 30 and then moves down towards the equator and then peters out, and then the new cycle with the reverse polarity comes in and decays away. And this butterfly diagram has been going on for a long time now. And that's, you can see that there's considerable variation in the strength of the activity in the 1960s and 1970s, when I first got interested in astronomy and was looking at sunspots and looking through spectroscopes. I had a very good time because I saw lots of activity there. Unfortunately, it's petered out a bit since then, and it's now there isn't quite so much activity for you guys, but there you go. But it's still, of course, there's still some spots going on there, and there's still flares and activity. This sort of long-term modulation seems to have been going on quite a lot. There was a long period when there was no solar activity, the Maunder minimum, and that lasted 70 years from about 1650 to 1720. The telescope was invented in 1610, so sunspots were spotted after that, and there were quite a lot of sunspots at that time, but then they all disappeared for that period, and then they came back again, and we're now seeing this solar cycle. And of course, there's loads of speculation going on now as to whether we're going into another Maunder minimum, because the activity cycle is going down quite steeply, but maybe it is, maybe it isn't. I mean, it has had low times before and then recovered, so yeah. So it's a bit like trying to predict magnetic reversals of the Earth. I mean, it could be that the Earth field is about to reverse. It may be that it's not. I mean, maybe we're about to go into a Maunder minimum, maybe not. The origin of the solar magnetic field is extremely controversial. I think on this is known from helioseismology. By the study of waves passing through the sun, we can actually work out what the speed of rotation speed of the sun actually is in the interior. That's the thing we can't do for Jupiter, because you can't see, unfortunately, any gravity waves or sound waves going. It can't detect any going into Jupiter. If you could, then we could do the same trick. But by looking at these waves and by looking at the Doppler shift of these waves, we can work out what the rotation rate is. And we know that in the convection zone, there's this broad pattern. It's going faster near the equator, and it's going slower in the polar regions. It's going more or less uniformly in the radiative zone. And there are these strong shear layers here and here where there's a lot of shearing motion going, so it's moving at one speed here and moving at a different speed there, so that magnetic field that got stuck between there would get stretched out in the azimuthal direction, and as it gets stretched out, it builds up new magnetic field, so that the traditional picture is that these shear layers here build up a very strong azimuthal magnetic field, and then that azimuthal magnetic field, because of the magnetic pressure, because the magnetic pressure exerts a force, the gas pressure is actually less, and therefore the density is actually less inside that, so it actually floats up. So that this magnetic field, by magnetic buoyancy, could float up here, and then it bursts out on the surface, and those are the sunspots that we see. And then it gets moved around here, and the poloidal field gets twisted around, and the poloidal field gets converted up there, and then the poloidal field comes down here, and it gets stretched out again for the next cycle. So that model is what's known as the conveyor belt model, and that was the sort of popular one when I actually wrote this slide, which was about 3 years ago. I went to this meeting in Göttingen last week. That's all yesterday's news, and the latest ideas are that it's the near surface shear layer here where all the stretching is actually occurring, not as we thought a few years ago down here in the tachocline. So we now have a new model, which is actually a sort of revival of the other models, but the view now is that it's actually the near surface shear layers here where most of the toroidal field is actually being maintained. So from the fact that it's changed over 3 years, you can tell that there are lots of different ideas coming up on the solar dynamo.
Mantle always was saying one of the models was the near surface.
Yeah.
Are there other people now saying the same?
Well, Schussler, yeah. So, I mean, Schussler was giving the talk there, and Robert Cameron, and they were making a very strong claim that that it's all dominated by the near surface shear layer. I mean, this was slightly news to me. There you go. So that's a possibility there. So you can see there's a lot of discussion and debate. There certainly is. I mean, the reason why people believed in this sort of flux transport model was there is a meridional circulation that you can see going around near the surface. So there definitely is a flow which could carry the poloidal field out. And as this magnetic field rises, it's azimuthal, but it gets twisted because of the Coriolis force, and that twists the flux loops. So that gives you a poloidal component, and that poloidal component then could get carried along by this mass motion here, and then it presumably has to dive down in there. So that model has been the most popular, but it's just that it doesn't seem to work terribly well. And there are various rather subtle arguments that Schussler was putting forward actually at this meeting, suggesting that it's actually much more likely to be here than it is to be down there. So anyway, there's the sun. So the basic principles are all the same. I mean, everybody believes that basically you've got to stretch out this field with the differential rotation, so the azimuthal field is created by that. Somehow that's got to be twisted into poloidal field by the Coriolis force, so the rotation is important. And then somehow that poloidal field has got to be stretched back into new azimuthal field. But exactly where the stretching is happening, how that field is being turned by the Coriolis force, all these are problems which are still very much up in the air. Okay, so that's that one. I'll we're a bit early for the thing, so I'll move on to the next one now. And I'm going to start talking about theory now. So let's put that away and go on. I've split it up into 3 lectures altogether. So now I'm going to talk about rotating convection. So now we've already seen that convection is important. I've mentioned several times that rotation is important, and indeed we've already discussed why rotation is important. It's basically because this term here, this is the Coriolis acceleration in a planet, is typically much bigger than this because the velocity u is really rather small in planets. Andy Jackson mentioned 5 times 10 to the minus 4 meters a second. And it's unlike, Jupiter is believed to be a little bit faster than that, perhaps 10 times faster than that, or maybe even 20 times faster, to be fair. But it's still rotating very, very rapidly, and u over omega d is extremely small, whichever planet you're talking about. So all of these planets, this term here is going to dominate these terms here. Or certainly this term here, and almost certainly that term there for most of the things well, not always, sometimes that comes back. I'll tell you about that later. So that's the Coriolis is very important. But so planets where we call rapidly rotation, where this term is sufficiently large that it can't be ignored and that it's doing something very significant. So Rossby number very, very much smaller than 1. Now in the Sun it's not the case. So the dynamics is sort of only marginally affected by the rotation, although we think it is in twisting this field, the azimuthal field round to the poloidal. Now, obviously you'll know that there's a centrifugal acceleration that goes along with the Coriolis acceleration, so why am I not talking about that? Well, the answer is that is a potential acceleration that can be written as the gradient of a scalar. Basically, that means it can be combined with gravity, so really it doesn't do anything different except just to change the shape of the gravity, at least to a sort of first approximation. So we're going to ignore that. Yeah, we still ignored in the Jupiter models that we've done. We haven't actually got that in. I mean, I'm sure somebody's going to put that in fairly soon, and it probably will make a bit of a difference because, well, Saturn particularly, it's nearly 10% of the gravity is due to the rotation. It will make a difference, yeah, but nobody's done it yet. Yeah, it does make a difference. So these are all the forces. So I hope we all know what we've got. Of course, the Lorentz force here, J cross B, the pressure force there, the buoyancy force, viscous forces, Coriolis and inertial accelerations over here, and we often talk about Coriolis force because if you just pop that